recording. Okay, so that brings us to 1.3, and it says right here, here are two pairs of quantities from a situation you've seen in this lesson. Each pair has a relationship that can be defined as a function. So they're giving us these two little situations here, and we're going to choose one of the quantities and express them as a function in this little activity. So my question is, which one of these two do we want to work on? Because we're not going to do both of them. We're just going to do one. So real quickly, someone send me something in the chat and tell me which one we want to do. All right, first one I saw was 2. So that's the one we're going to do. So you can take your pencil and you can just mark off this first one. Okay, we're not going to do that. So it says, here's our quantities that we're going to be working with. We're going to be working with time in seconds since the owner left, and the total distance in feet the dog has walked while waiting. Okay, so time and distance are two main variables for the situation. Okay, so it says in that function, which variable is going to be your independent and which one is going to be your dependent. So we talked about these new vocab words a little bit in class on Tuesday. So who can tell me which variable represents the independent variable? Is it my X or my Y?
X.
It's my X. Okay, so we weren't given anything to tell me which one of these two variables is going to be my X or my Y, and it's not written in that little format. Blank is a function of blank. So how are we supposed to know which one is my X and which one is my Y? Well, I will tell you this: anytime you're given your variables and time is one of the two, 9 times out of 10, that variable will always be your X. Okay, so anytime time is one of the variables that you're working with, it will almost always be your independent or your X. Okay, so on number 1, we're going to write independent. Okay, so what variable represents our independent variable?
X.
Which is what? All right, now we have our dependent variable. All right, so if our independent is our X, then what is our dependent?
Y.
The Y value. Okay, so what is the dependent variable for this situation?
Total distance.
The total distance. All right. Now that we have our independent and dependent variables, we can write it in that sentence form that we talked about in that last activity. So it tells us blank is a function of blank. Now, when we see it written like this, which variable always comes first?
Y.
the y value or the dependent. Okay, so if we were going to write that in sentence form, now we just have to explain what our y variable is. So total distance the dog walked is a function of, okay, so that brings us to this last variable. What variable comes at the end?
X.
The x. So total distance the dog walked is a function of what?
Time in second.
When we write it in that sentence form, we need to be as detailed as possible. All right, and I know it might be kind of confusing that the y value comes first in that little phrase, but whenever you see this little phrase is a function of, it actually means when you're saying that, you're saying depends on. Okay, so you're saying that this y value, the total distance, depends on how much time has passed. That's what it means when you're saying is a function of. All right, moving right along. So good job so far. Those are some big concepts that we've just scratched the surface of, our number 1 and number 2. All right, so we get to number 3 and it wants us to sketch a possible graph of the relationship. Be sure to label and indicate a scale on each axis and be prepared to explain. All right, so once again, we need to define our x and our y. So what is my x-axis going to be labeled?
Is this the graph going to be like of the problem we just did?
Yeah, we're still on this situation here.
Okay, so time in seconds.
Time in seconds, perfect. Okay, so that is our x-axis. So what is our y-axis going to be labeled?
Distance.
The total distance. And it's measured in feet. You want to put that. All right, now we have labeled the graph, check. All right, but we still need to indicate a scale. Okay, so we know that when we're scaling a graph, that just means we're numbering it off. Okay, so in the situation that we're talking about, it's that same situation where the dog was tied to the post when the owner went into the store. And it said that only a couple minutes had passed. Okay, so when we scale this, we just need to scale it to represent a couple of minutes, but we have to do it in seconds. Okay, so what could we count by to represent, to make sure that we get all those couple minutes included?
30 seconds.
We could go by 30 seconds. So we have 30 seconds, 60, that's 1 minute, 90, 120, that's 2 minutes, 150, 180, that's 3 minutes, 210 and 240, that's 4 minutes. That works. Is that the only way we could have scaled it?
No.
No, we could have scaled it. We could have counted by 20s. We could have counted by 25s, but that works. Perfect. Now we're talking about distance in feet. that the dog was away from the post or that he walked around. Now, we did know one important piece of information when we were doing this. We knew the length of his leash. How big was his leash? Do y'all remember that?
Was it 5 feet?
It was 5 feet. Okay, so we have to have at least 5 feet. So what can we count by now for the distance?
Twos.
We could count by twos, but we have enough room. We could even count by just ones. Because he can't go past this line anyways. So that way it's not all together. Sorry, this kind of looks sloppy right there. All right, now they didn't give us any information about where the dog was at any given time. So when we draw our graph, we just have to make sure that it is a function because they told us right here, they are a function. So when we're doing it, we can just say the dog started, right up against the pole because we don't know anything else. And he just started, walking around. Would that be a reasonable graph for this situation? Yes or no?
Yes.
Oh, yes. Okay, I also see a chat. 1 second. Yes. Okay, now I want y'all to tell me, would this be one? Now, y'all don't have to draw this one, obviously. Would this be considered one that works for the situation?
No,
Why would this not work?
because it goes back. There's more than one point.
Okay, if I were to get my vertical line test and I were to drag it across this, whoops. And I were to drag it across this line, then right there, when my pencil was on that graph, I could see that right there, and right there are all touching my vertical line, meaning that at about 45 seconds, the dog was simultaneously 1 foot, 2.5, and 3.5 feet away from where he started. Is that possible?
No.
No.
No, that's not possible. We can't do that. Okay. So that wouldn't work for my graph. So it just has to be, everyone could have drawn it differently as long as it's still a function. Okay. So, like that, something like that. Okay. All of them could have been different as long as it just passed the vertical line test. Yeah. All right. So that brings us to the lesson 1 summary. This is on page 134 at the bottom. It says a relationship between two quantities is a function if there is exactly one output for each input. Okay. So exactly one y value for every one x value. All right. So in those situations, we refer to the input as the independent variable. And we refer to the output as the dependent variable. All right, so now we're going to look at a situation in this summary between the amount of time since a plane takes off and the plane's height above the ground. All right, now they have not told us which one is our X and which one is our Y value, but I can see that one of my variables is time. So time is more than likely going to be what
X.
variable?
X.
My X, or my input, or my independent variable, which would make the plane's height my Y. Okay. So moving on to this first bullet point, it says these two quantities form a function if time is the independent variable and height is the dependent variable, which is exactly what we said. Okay, time would have to be our X. The height would have to be our Y. And the reason that is because at any amount of time since takeoff, the plane could only be at one height above the ground. So for example, we take off and we're in the air, we're at 50 seconds after takeoff. At that exact moment, the plane is 180 feet above the ground. Okay, that makes sense. Okay, you're at that exact height. Now, at that exact moment, it cannot be at 180 or 95 feet above the ground at the exact same time, because that one input of 50 seconds can only have one output at 180 feet. Okay, it can't have multiple heights. Does that make sense?
Yeah.
Okay, so big takeaway: for any input, there is only one possible output. So the height of the plane is a function of the time. And there's that little phrase that we've been talking about, is a function of. So we can see that that value before is our Y, and the value that comes after is our X. Okay, so now we've come to this one. It says the two quantities do not form a function, however, if we consider the height as the input and time as the output. Okay, so now we're switching them. Okay, well, why does time always have to be the input? Well, we're about to prove it. It says it cannot be that way because the plane can be at the same height for multiple lengths of time. Okay, if you've ever been in a plane or you know how they work, you know once they get to their highest point, they're kind of coasting for a pretty long time. They're at the same height in the air for a lot of the time. So, for example, when the plane is 1,500 feet above the ground, it is possible that 300 seconds have passed, 425 seconds have passed, and 275 seconds have passed. Okay, that's entirely possible. So, for any input, there are multiple outputs in this situation. So the time since takeoff is not a function of. So because this input has multiple outputs, it is not a function. All right, it says functions can be represented in many ways. We can represent them with verbal descriptions. For example, blank is a function of blank. We can represent it by a table, like when we were talking about the bagels and their prices. We can represent it by a graph, like when we graphed the dog walking around the post. An expression or an equation, we haven't got there yet, or a set of ordered pairs, like on a graph. When a function is represented with a graph, each point on the graph is a specific pair of inputs and outputs. Here's a graph that shows the height of a plane as a function of time. So because it's written in that little phrase, we know that the height of the plane is our y value, which it is. And we know that time since takeoff is our x, which it is. Okay, so we have this point right here on our graph, 125, 400. And that point is just, we're just going to read what the axes are talking about. The point tells us that 125 seconds after takeoff, the height of the plane is 400 feet. Which makes sense. All right, we have one more problem we're going to do, and then we will be done for the day. Okay, now this next question is not in your book, but it's such a good review. So while a lot of y'all are going to try to check out, please pay attention because it kind of like sums up every single thing we've talked about in this first lesson. And it's going to be a good review right before I assign your homework. Okay, so let's look at it. Now, again, this is not in your book, so y'all just pay attention to your screen. It says the parent is using a garden hose to fill up a small inflatable pool for her young child. Now, whether you've had an inflatable pool or not, we've all we either know how they work or we've actually swam in one. So just imagine that in your head. The pool has a capacity of 90 gallons. So when it is all the way filled up, it holds 90 gallons. It says she turns the water off after 5 minutes. Okay, so we're filling up the pool for 5 minutes and then she turns the water off, but she leaves the hose in the pool for another 3 minutes before taking it out and putting it away. Okay, so in this situation, there is a relationship between the gallons of water in the pool and the 8 minutes since the parent started filling the pool. And it can be seen as a function. All right, so now get ready to participate in this. It says in the function, which variable is my independent and which variable is my dependent. Okay, so again, our two variables are gallons of water and minutes. All right. Between those two, which one is normally always going to be our independent variable? The minutes, the time, okay? So my independent is going to be time in minutes. All right, so then what would my dependent variable be?
Gallons of water.
Gallons of water. Perfect. Now, we want to write that in our sentence form. So blank is a function of blank. Okay, which variable always comes first when we're writing it like this?
X.
Not our X.
Independent.
The Y value comes first.
Sorry.
No, you're good. Okay, because remember, this little phrase means depends on. Okay, so the y value depends on the x value. Okay, so to write that in a sentence, we would say the gallons of water is a function of time. All right, so far so good. Hopefully y'all are all paying attention and understanding this. All right, so number 3, we're going to sketch a graph of it now. We need to label it and scale it. So the first thing I always start with is I need to label my x and I need to label my y axis. So what is my x axis going to be? What did we just say? That's my independent variable. What is it going to be?
Time.
Time in minutes. All right. So if that is my x axis, what is my y axis going to be?
Gallons water.
Gallons of water. If you are sending stuff in the chat, it takes me longer to read those because I have to like go and open them. So sorry, I promise I'm not ignoring you if you're sending it in the chat. Okay, so we have labeled it. Now we need to scale it. So we have time in minutes. So how many total minutes took place in filling up this pool? She turns off the water after 5 minutes, but she leaves it in there for another 3 minutes. So how many total minutes are taking place? 8. Okay, so I'm going to come down here. So how could I count this to fit 8 minutes in this little section?
There's enough to go by once.
There is enough to go by 1, so that's what I'm going to do. All right, now we have gallons of water. So how many total gallons could we fit in this swimming pool? Does anyone remember?
90.
90 gallons. Okay, so that needs to be at least my maximum when we're scaling it. So how could I count off this scale to where I could at least get to 90? I could go over like on my scale, but I need to at least get to 90 there. So what can I count by?
Didn't you go by 15s and have 90 at the top?
Okay, I can count by 15. So I have 15, 30, 45, 60, 75, 90. Perfect. Now we have created our graph. Now, this time, they do give us information about what my actual function is going to look at. So when I graph it, I actually have something to go by. So we're filling up this pool. So obviously the gallons are going to start filling up as soon as the time starts. So before time starts, how many gallons of water are going to be in this pool?
0.
0. So my graph is going to start down here at the origin, right? Okay, then we're filling it up, and then after 5 minutes, she turns the water off. So when we're at 5 minutes down here, so when I'm at 5 minutes right here, how many gallons of water needs to be in the pool?
90.
90. Okay, so I have to connect this dot down here to this dot up here. So when we're filling up a pool, is the gallons of water increasing and decreasing like this?
No.
To get there? No, that wouldn't make sense. We know that when we're filling up a pool or a bathtub or anything really, the water is increasing at a constant rate, right?
Right.
So it's just going to increase like this, like a straight line. Okay. So far, does this pass the vertical line test?
Yep.
Yep, it works. Now, we're not done because after she turned the water off, what did she do with the water hose?
She left it in there for 3 more minutes.
She left it in there for 3 more minutes. So during that 3 minutes, what's happening to my gallons of water? Is it increasing or
It's staying
decreasing?
the same.
It's staying the same. So what's the next section of my graph going to look
Straight
like?
line across.
Just a straight line. Ah, almost made it through a whole lesson without doing that. Okay, I don't know. Okay, whatever. All right, it's just going to be a straight line right across for how many minutes?
3 more.
3. 1, 2, 3 minutes, and then we stop. I don't know why it's erasing it, but yeah. And there is our function. And if we wanted to test it out, oh my gosh, 1 second. If we wanted to test it out, we just have to get our pencil and then test it out with our vertical line test. Are all my inputs, do they only have one output? Yes, it does. So it would be considered a function.